In the final video in this series reviewing important concepts from chemistry, we're going to look at a different way of representing organic molecules than the traditional Lewis structures such as the one we see here. So this 3-carbon compound here is an example of a type of organic compound that we call hydrocarbons, not surprisingly because it only contains hydrogen and carbon within its structure. This is a relatively simple hydrocarbon, and if we were to replicate this Lewis structure like I'm doing here, we can see that it doesn't take particularly long to fill in all of the atoms and all of the covalent bonds that make up this structure here. So if you paid attention and actually timed how long it took me to draw this, probably between 5 and let's say 8 seconds liberally, let's see if we can cut down the time of that. So put that time that it took me to draw this Lewis structure in the back of your mind. Now the reason why we want a quicker way of representing structures of organic compounds, that being any compound with carbon as the basis that mostly contains hydrogen and oxygen, we can see that the structures of organic molecules get very, very complicated, especially as they get larger. So rather than drawing the full Lewis structure, which I did here, I'm going to show you how to draw a very simplified structure that still communicates all of the information. And that's the structure. So, regardless of how quick it took me to draw the full Lewis structure, I was able to draw this one here in less than a second. Now, because this structure is literally just 2 lines, not surprisingly, we call this a line structure. So a line structure is a very simplified form of an organic compound, and basically what it does is it represents every bend in the lines, and every end of the line tells us that there is a carbon atom there. So the 2 ends of this line structure represent the 2 carbons on the end of this hydrocarbon, and the bend in the line there represents the carbon in the middle. And basic chemistry knowledge tells us that carbon is able to form 4 bonds, so the only bonds that are shown are represented by the lines themselves. So this is a carbon-to-carbon bond, and this is a carbon-to-carbon bond, and all of the other bonds are assumed to be a bond between carbon and hydrogen, with the assumption that carbon is able to make 4 bonds. So that means that this carbon on the end is going to be bonded to 1, 2, 3 invisible hydrogens, and so is this one here, 1, 2, 3. But because the carbon in the middle is connected by 2 lines, each representing the carbon-to-carbon bonds, there would only be 2 hydrogens like that. And we can see same chemical structure communicated by a much more simple example of a structural diagram like this. Now, if we want to show how effective line structures can be, we can try to replicate the more complicated structures that we find below. So this particular hydrocarbon contains 1, 2, 3, 4, 5, 6 carbons. So let's see what a line structure would look like there. So I start with my first carbon. There's 1, 2, 3, 4, 5, 6. Just to quickly double check, we look at our full structure and we don't see any other element other than carbon or hydrogen, and there are 6 carbons, and we know that every end and every bend in a line structure is a carbon. So double checking, 1, 2, 3, 4, 5, 6. Simple as that. If we take a look at the larger hydrocarbon here, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, and they've actually given us the design for what our line structure is going to look like. So if we just copy that with the same idea, 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember that every end and every bend is a carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there are no other elements in this structure other than hydrogen and carbon. Looks like we're good. Now, this next example here, we see our first example of a compound that has elements that are not carbon or hydrogen, and we see them branching off to the side. So we see a nitrogen here bonded to two hydrogens, and we see the carbon on the end is double bonded to one oxygen and single bonded to another. So let's go ahead and draw the carbons first. So we see there are 1, 2, 3 carbons. So let's go 1, 2, 3, just like that. And if we consider this carbon here to be the one only with hydrogen, we don't need to add anything there because all of the carbon to hydrogen bonds are understood to be invisible. So the middle carbon here, we need to actually draw another bond here, but for the first time we need to add an element that isn't carbon or hydrogen. So we're going to put the nitrogen in like that, and the nitrogen is bonded to two other hydrogens like this. Finally, the last carbon, this one on the end, is double bonded to an oxygen. So let's put the double bond like that with an oxygen here, and then one more single bond for this oxygen here, and this oxygen is bonded to a hydrogen, and there is what a line structure looks like for an organic compound that contains not just carbon and hydrogen, but other elements as well. And you can see all of the carbons are either represented by the end of a line or a bend in the line, and all of the other elements are explicitly written out. Now, our last example here is interesting because the carbons are not in a chain, one after the other after another. They actually form a ring like this. But again, the rules still apply. Any bend or any end in the chain is a carbon, and if bonds are not shown, it's assumed that they're all going to be hydrogen. So let's draw the ring first. We see that it's roughly hexagonal, which means it's going to have 6 sides. If we draw the first 3 carbons, 1, 2, 3 like this, and then the bottom vertex of our hexagon is not going to be a carbon because there's a nitrogen here, and we see the nitrogen is bonded to a hydrogen like this. Then we also need to pay attention to double bonds versus single bonds. So there's a double bond here, so let's just draw a second line. Then this nitrogen is connected to another carbon like that, which we don't need to write. And if we complete our hexagon, this carbon here is bonded to a nitrogen here, which connects back to the top carbon with a double bond like this. Then all that we need to do is fill in the other elements outside of the ring. So our top carbon is connected to a nitrogen that has 2 hydrogens on it like this, and then the bottom left carbon is connected to a double bonded oxygen like this. So we can see line structures work perfectly well to represent organic compounds in chains or organic compounds as part of a complex ring structure, both of which we will see in more detail in the biochemistry unit. To confirm your understanding of how to draw line structures, you can try taking the 5, 6 compounds that are on the next page and converting them from their full Lewis structures that we see here into their line structure form next to it. And once you've completed this, as long as you have the understanding, you should be ready to begin the actual biochemistry unit with your foundations in chemistry reviewed.